100 million years ago, the ancestor of every snake alive today was just a lizard. 4 legs, ordinary teeth, nothing special. Today, that same lineage has produced an animal that can detect a single degree of temperature change in total darkness, swallow prey 3 times the width of its own head, and kill an elephant with a few drops of liquid smaller than a teaspoon. This is not an accident. This is one of the most extreme transformations in the entire history of life on Earth. Today, we are breaking down exactly how snakes evolved into the perfect killing machine, piece by piece, system by system. Welcome to Scales and Tails. Let's get into it. How snakes lost their legs and gained an advantage. The first thing that had to happen was the strangest. Snakes used to have legs. Fossil evidence shows clear leg bones in early snake ancestors. Over millions of years, those legs disappeared almost entirely. Some modern snakes, like boas and pythons, still carry tiny leg remnants called spurs near their tail, a leftover signature of where legs used to be. Losing legs sounds like a disadvantage. It is actually the opposite. A legless body can fit into spaces nothing else can reach. Burrows, cracks, tight tunnels underground where prey hides and predators cannot follow. It allows a snake to move in total silence, with no footsteps to give away its position. And critically, it freed up the snake's entire skeleton to evolve in a completely different direction, towards something built almost entirely around the mouth, the jaw, and the delivery of venom. Losing legs was not snakes giving something up. It was snakes trading mobility on land for becoming an ambush predator that nothing sees coming.
The origin of venom, a modified form of spit. Here is something most people do not know. Snake venom did not appear out of nowhere. It evolved from ordinary saliva. Every animal's saliva contains small amounts of proteins that help with digestion. In the ancestors of venomous snakes, natural selection slowly modified these saliva proteins over millions of years, turning them from simple digestive aids into something far more dangerous. Scientists now believe the genetic toolkit for venom may have existed in snake ancestors long before venom itself appeared, meaning the building blocks were already there, waiting to be repurposed. And critically, research shows venom evolved primarily as a hunting tool, not a defensive weapon. Snakes did not develop venom to protect themselves from predators. They developed it to subdue prey faster and more efficiently than physical strength ever could. A bite that used to just hold prey in place slowly transformed into a bite that could paralyze, dissolve tissue, or stop a heart entirely, all without the snake needing to fight or wrestle anything. Today, snake venom contains incredibly specific toxin families. Some attack the nervous system, some attack blood and tissue, some attack muscle directly. Each one evolved to target a precise weakness in prey, refined again and again across millions of generations.
How fangs evolved, not once but multiple times. This is one of the most remarkable facts in all of snake biology. Fangs did not evolve just once in snake history. They evolved independently, multiple separate times in different snake families. Vipers, elapids like cobras and mambas, and rear-fanged snakes all developed venom delivery fangs on their own through completely separate evolutionary paths. This is called convergent evolution, when nature arrives at the same brilliant solution more than once because it simply works. Researchers studying snake embryos discovered something fascinating. Both front fangs and rear fangs develop from the same region of the embryonic jaw, meaning the genetic blueprint for building a fang was already present deep in snake DNA, ready to be activated again and again whenever a species needed it. And fang shape itself evolved to match specific prey. Snakes that hunt soft-bodied prey like mammals developed long, slender, razor-sharp fangs built for deep penetration. Snakes that hunt tougher prey developed more robust fang structures built to withstand greater force. Every fang on Earth today is a precision tool shaped by exactly what that snake evolved to kill.
The jaw that unhinges, how snakes eat prey larger than their head. Here is a popular myth to clear up immediately. Snake jaws do not actually unhinge or dislocate. What they have is something arguably more impressive, a jaw built from multiple independently moving bones connected by extremely elastic ligaments. Most animals have a jaw that is essentially one rigid structure. A snake's jaw is built more like a flexible frame, where the left and right sides can move almost completely independently of each other. This allows a snake to walk its mouth forward over prey in alternating movements, one side gripping and pulling, while the other side releases and advances, slowly working an entire animal, sometimes 3 or 4 times wider than the snake's own head, down into its body. The skin and skull connections stretch to accommodate the meal, then return to normal size afterward. This single adaptation solved an enormous evolutionary problem. Without arms or claws to tear food into smaller pieces, a snake needed another way to eat large prey whole. Evolution did not give snakes the ability to chew. It gave them a jaw that could become temporarily enormous instead.
Heat-sensing pits hunting in complete darkness. Some snake families evolved something that puts them in a category almost no other animal on Earth occupies. Pit vipers, including rattlesnakes, copperheads, and many others, developed small heat-sensing pits located between their eyes and nostrils. These pits can detect infrared radiation, essentially allowing the snake to see the body heat of warm-blooded prey as a kind of thermal image, even in absolute darkness, even with the snake's eyes completely closed. This sense is so precise that some species can detect temperature differences of a fraction of a single degree from a distance. It means a pit viper hunting at night does not need light at all. It is tracking a living heat signature moving through the dark, completely independent of normal vision. Combined with their ability to sense ground vibrations through their entire body, this gives certain snakes an almost supernatural awareness of prey movement long before any visual contact is made. Nothing has to see you coming if it can already feel exactly where you are.
Why some snakes have no venom at all? Not every snake chose this path, and that is just as fascinating. Most snake species alive today are actually non-venomous. Constrictors like pythons and boas evolved a completely different killing strategy, overwhelming physical strength and precise muscular control instead of chemistry. A large constrictor can apply pressure strong enough to stop a prey animal's heart and circulation almost instantly, without needing a single drop of venom. Other non-venomous snakes rely purely on speed, surprise, and raw grip strength to subdue smaller prey before it can react. This tells us something important about evolution itself. There is no single correct way to become a perfect predator. Some snake lineages specialized entirely around venom chemistry. Others specialized entirely around muscle and pressure. Both paths, refined over millions of years, produced equally devastating results, just through completely different mechanisms. The diversity of solutions is in many ways more impressive than any single one of them on its own. The arms race between snakes and their prey? Evolution does not happen in isolation. As snake venom became more lethal over millions of years, prey species were not standing still either. Some animals, like the mongoose and the honey badger, evolved genetic resistance to specific neurotoxins, developing nerve receptors that venom struggles to bind to effectively. In response, certain snake venoms have continued evolving in turn, growing more complex and more concentrated, especially in regions where resistant predators exist. This creates what biologists call a coevolutionary arms race, two species locked in a multi-million-year cycle, each one constantly adapting to counter the other's most recent advantage. It is the same evolutionary pressure responsible for nearly every extreme adaptation in nature. The deadlier the prey's defenses become, the deadlier the predator's weapons must become to keep up. Snake venom did not reach its current potency by accident. It reached it because the alternative was starvation.
The most evolved killer alive today? Put all of these systems together and you get something extraordinary. A body with no legs, built for total silence and access to spaces nothing else can reach. A jaw engineered to consume prey several times its own size without chewing. Venom refined over tens of millions of years to target the precise biological weaknesses of specific species. And in some species, the ability to literally see heat itself and strike with pinpoint accuracy in absolute darkness. No single random mutation created this. It took an almost unimaginable number of generations, each one slightly more efficient than the last, building toward a design so effective that it has barely needed to change in millions of years. Sharks are often called perfectly evolved predators, so are crocodiles. But very few animals on Earth combine chemistry, mechanics, and sensory perception into a single integrated killing system the way a snake does. This is not a monster. This is simply what happens when evolution is given enough time to perfect a single devastatingly effective design.
So, next time you see a snake, remember you are not looking at a simple animal. You are looking at the end result of over 100 million years of refinement. Every part of it, from the missing legs to the heat sensing pits to the venom in its fangs, exists because it worked, generation after generation, better than anything else that came before it. Drop a comment telling me which adaptation surprised you the most. Subscribe to Scales and Tales for more wild snake facts every week. See you next time.